welcome to the fourth episode of Benjamin at Work here at Plain Space Design. Well, we've got some old business to take care of today, but we're finishing up on the ellipse because, as I mentioned earlier, we do have a lot of ideas coming through, 5 or 6 ideas a week, and it's been 3 weeks, so that means about 15 ideas has passed by that we have not shared with you. So we're going to go ahead and finish up on the ellipse today and introduce some of the newer ideas. I'm going to start with the old business, which is some of the things that I would like to close out on the ellipse problems. If you recall, in the previous episode, we ran into some problems with our formula for the ellipse when we were working in Excel. I mentioned that perhaps one of the causes of that problem could be inefficient coding of the equation. So today we're going to discuss what that really meant. It is important how you formulate your equations or how the expression is written depending on the purpose you want to use it for. In our context, where we were doing computations in a computer program, efficiency is sometimes an important factor. So here we're looking at the 4 equations for the ellipse. They're all the same equation, however. At the top, we have the standard form of the equation for the ellipse, and this is used whenever you want it to be obvious to someone what type of curve you are working with. Number 1 equation says this is the ellipse to all people who are familiar with this expression. And in number 2, we were solving the equation for the ellipse as a function of y equals a function of x. Therefore, this is the same equation but expressed for a different purpose, and that is when you want to create a table as we were doing by plugging in various values of x and finding out what values of y will result. Now when you look at equation number 2, you will notice that in a computer you would have to do a lot of squaring of the numbers. You have a b squared, you would have to square x, you would have to square a, and then you would have to divide x squared by a squared, and then do a subtraction and take the square root of everything. This is what I meant by inefficient coding. There's a whole lot of operations going on that we could have taken out. And I'm going to show you that in equation number 3. Notice that in equation number 3, the b squared is out of the radical, so it already has been operated upon, and that's one operation taken out of the calculation. And you notice also that you do not have to square x or a. Because of the parentheses, you will divide those numbers in their unsquared form and then square the result. So in equation number 3 for the ellipse, there is only one squaring operation, one subtraction, and one square root, and a division. So this reduces the probability that a machine would be making an error. Of course, a powerful computer would not really care which way, 2 or 3, was used. However, some computers are not that powerful. They're just getting by, and efficiency helps. I think my notebook computer may be in that class, but this is still not the determined cause of the problem. It could still be Excel, or it could have been this. So if you have a version of Excel, maybe you should try coding this into your Excel and see what type of results you get, whether the efficiency mattered. Now the fourth equation is also the same equation for the ellipse that we started out with. So all of these are the same equations. They're just expressed in different ways. And with number 4, we satisfy something that we said was a goal in our previous work, and that is to mix the two circles and create an ellipse. And equation number 4 jumps right into the fray of that. This is a mixture of two circles, one with radius A and the other with radius B, and see how the numbers are combined in pairs. The A mixes with the Y, the B mixes with the X, and the A mixes with the B. So this is the goal that we were trying to achieve, and expressing the equation for the ellipse in this way puts us a step further along the road of accomplishing that goal of combining two circles, a major circle and a minor circle, and getting an ellipse. Another item from last week has to do with the table of values that we generated for the ellipse. Here you see the top rows of the table and the bottom rows of the table with the middle rows left out. I want to call your attention to what happens when x equals 0 and y equals 1 here at the top of the table. That is when we are on the minor axis. When we plug these values into the major axis circle formula, as we call it the major circle, we get a value of 0.25. That means that this major circle only gets to 1/4 of the amount that it needs to reach to be part of the ellipse. Now that is no coincidence though, because when you get to the bottom of the table here, where the x value is 2 and we're at the edge of the semi-major axis, y will be 0 there. And when we plug this 2 and 0 into the minor circle formula, we get a value of 4. In other words, the minor circle generates a value 4 times larger than it needs to have generated to be a part of the ellipse. So we see that there's a ratio of 4 to 1 between the two circles and how they respond to the points that it received from the ellipse. If you think about it, the major axis is 4 times larger than the semi-minor axis. And so when we get a point that is on the semi-minor axis, it gets you to only 1/4 of the way, 1/4 of the way that you need to go. On the other hand, the semi-minor axis is 1/4 the length of the major axis. And so when you get a point from the ellipse and put it into the minor axis formula, you get to a point that is 4 times larger than you need to be in order to be on the ellipse. So this relationship is a pattern, and though it is not easy to see that pattern and not easy to understand what it means, it is something that I felt was very interesting, was worth mentioning. Perhaps someone digging into that pattern may find even more that they can share with us. Now it's time for the new business. As I mentioned earlier, a lot of ideas have come through here since we began the ellipse problem, but now I am going to just pick one that seemed to have set the tone for most of the work and report that to you. As you see now, my notes are a bit different. I'm not doing handwritten notes anymore. I'm in the digital age, so I'm digitizing my operations inside of my daily workspace, and therefore I have digital notes, well typed and whatnot. So the one that I have chosen came in around the 18th of June, and it's about mutual forces. And I picked this one because we are now going back into working on propulsion dynamics related work. And the most important thing that occurred to me at this time was that in order to master some of the propulsion systems that I'm designing, someone would have to face the challenge of working with mutual forces inside of systems, something that really has been ignored because the normal propulsion system, the common propulsion system, those that we know, do not have to deal with mutual forces except in structural contexts. But here, mutual forces are dealt with in the context of propulsion, the actual process of getting propulsion. That's probably the biggest obstacle that we have to overcome. So if you're familiar with some of the videos that I have placed online describing one of the propulsion systems, the translational oscillator, then you will see how mastering mutual forces is required in order to engineer this system properly. So I have a statement here about mutual forces that came to my mind on the 18th, and it says the biggest challenge for inertial propulsion development is working with mutual forces. The question is, how can such a configuration of forces serve unidirectional translation? The only known method is to bias the inertia distribution to be less in the desired direction of motion and more in the opposite direction. A simple rule was, if going forward, be lighter, and if going backwards, be heavier. And so that is what we worked out here over uh, many, many years, starting in the 80s. We have been dealing with this problem, and when we're building the structural components and actually making prototypes and testing them, now we have to face mutual forces in order to get our best result. So our future discussions, starting with today, will focus on propulsion dynamics again, and I will show you the work that I am doing today, right here at Plane Space Design, related to that topic. So, in the interest of keeping these within a time limit, this episode is a wrap. If you should happen to decide to follow one of the strategies that we laid out here and achieve something of note, perhaps even solve the problem, please comment here, share what you have done with us. We would really appreciate having your input.